Let's continue with our lecture on mathematical physics. Today we are going to cover Cauchy Riemann condition and related problems. This is a part of a course Mathematical Methods PH3103 at IISER, Calcutta. Before going into Cauchy Riemann condition, first look at the analytic function. Let's look at the definition of analytic function at a given point z0. A complex function w is equal to f of z is analytic at a point z0 if f of z is differentiable at z0 and at every point in some neighborhood of z0. So these two are conditions. It's not just sufficient the function is differentiable at that point. It has to be differentiable in some neighborhood around z0. So that is what we call analytic function. So we have a point and we have a neighborhood where you have a f of z and f of z prime should exist not only at a point z0 in a neighborhood. Extending this, a function f of z is said to be analytic in a domain if it is analytic in every point in the domain. So we can extend this to a larger region. Then we have a domain. Then it should be analytic at every point in the domain. That means at every point in the domain we should be able to construct a neighborhood such that f of z and f of z prime exist. So that is what we say it is analytic in the domain. We can further extend this analytic in the entire complex plane. In such case, it is called the entire function. Now the same definition is extended to the complete complex plane. If the function is analytic at every point in the complex plane, then we call it an entire function. Let's look at one of the important theorem in the functions of a complex variable, that is Cauchy Riemann condition. Let f of z is equal to u of xy plus I v of xy is differentiable at a point z is equal to x plus iy. Then at z, the first order partial derivative of u of xy and v of I exist and satisfies the Cauchy Riemann condition given by partial derivative of u with respect to x must be partial derivative of v with respect to y, and partial derivative of u with respect to y must be equal to minus 1 into partial derivative of v with respect to x. So this is an alternative way of figuring out if the function is differentiable or not. In principle, one should be doing it from the first principle by taking the limit, taking arbitrary curves and ensuring that all of them the same limiting value of a differentiation. However, it is a tedious process. There is a simpler way of just checking the Cauchy Riemann condition. Condition is that if the function is differentiable at the point x plus iy and if the partial derivative of u of xy and v of I exists, then it should satisfy the Cauchy Riemann condition, that is the partial derivative of v with respect to x must be equal to partial derivative of v with respect to y, and partial derivative of u with respect to y must be equal to minus 1 into partial derivative of v with respect to x. Let's look at the proof. It's fairly straightforward, though looks a bit cumbersome. The idea is very simple. You define the differentiation using the first principle and approach it to the two different paths, that is along the real axis and imaginary axis, and then obtain differential for the both paths and then equate them to equal, and then we would get the Cauchy Riemann condition. Let's start with the definition of derivative, that is f prime of z is equal to limit z going to 0 f of z plus delta z minus f of z into delta z. Now we also have f of z is equal to u of xy plus I times v of xy. we have z as a x plus iy and delta z as a delta x plus I delta y. We can substitute this in the definition of f prime, and then we would get f prime is equal to limit delta z going to 0, u of x plus delta x, y plus delta y plus I into v of x plus delta x, y plus delta y minus u of x minus I times v of xy divided by delta x plus I times delta y. Now, in the first case, we take the limit along x-axis, that is, we take delta z to 0 along x-axis. In this case, delta z becomes delta x and delta y is 0. So we substitute again back into the definition given here, and then f prime z is equal to u of x plus delta x y minus u of xy divided by delta x plus I into v of x plus delta x y minus v of xy divided by delta x. Not only substituted in this equation and separated the real and imaginary part. Now we take the limit delta x going to 0, and that we know that this is essentially partial derivative of u with respect to x, and the second term is a partial derivative of v with respect to x multiplied by I. So that is how we have f prime of z is given by partial derivative of u with respect to x plus I times partial derivative of v with respect to x. Let's call this equation A, and let's continue by taking the other path, that is go to delta z is equal to 0 along the imaginary axis. So we have a definition, all the substitution. Now we take a different path. We take delta z0 along y-axis, that is delta z is equal to I times delta y, and delta x is 0. Now we substitute back and separate real and imaginary parts again. Then we have f prime z is equal to limit y going to 0, limit y going to 0, u of x plus y plus delta y now minus u of x divided by I delta y, because we are coming along the imaginary axis. I getting cancelled here in the numerator and denominator. The second term is simply v of x, y plus delta y minus v of x divided by delta y. Now again we know that this is a partial derivative of u with respect to y multiplied by minus I plus partial derivative of v with respect to y. That is the value of f prime of z, and we call it equation B. Now we can get the Cauchy Riemann condition. If the derivative of f of z exists, then these two values we are getting in the equation A and B should be equal. That is, f prime of z must be equal to minus I into partial derivative of u with respect to y plus partial derivative of v with respect to y must be equal to partial derivative of u with respect to x plus I times partial derivative of v with respect to x. Now we equate real and imaginary part. We get Cauchy Riemann condition as a partial derivative of u with respect to x must be equal to partial derivative of v with respect to y, and partial derivative of u with respect to y must be equal to minus 1 into partial derivative of v with respect to x. Let's look at the quick example. In this case, we take a function f of z is equal to x plus 4y. We already done this example and shown that it is not differentiable. So that means it is not analytic at any point. In this case, you have a u is equal to x, v is equal to 4y, du by dx is equal to 1 and dv by dy is equal to 4. This can't be equal, so it cannot be analytic. On the other hand, we have du by dy is equal to dv by dx is equal to 0. This is okay, but both of the conditions have to be satisfied. So that means that this is not an analytic function because one of the condition is not satisfied. Let's look at another example. Let's look at the function f of z is equal to z square plus z. This is a polynomial, so it should be analytic in the entire complex function, or it is an entire function. So let's write down in terms of x and y. F of z is equal to x square minus y square plus x plus I times 2xy plus y. Here we have u is equal to x square minus y square plus x and v is equal to 2xy minus y. Again, let's take a partial derivative of u with respect to x. We find that it is a 2x plus 1, which is same as partial derivative of v with respect to y. So in this case, first of the Riemann condition is satisfied. Let's look at the second one. Derivative of u with respect to y is equal to minus 2y, which is same as minus 1 into derivative of v with respect to x. So both the Cauchy Riemann conditions are satisfied. So this function must be an analytic. So which we already know, all the polynomials are analytic function. It also satisfies the Cauchy Riemann condition. Let's look at another example. We have lots of examples in this case. Let's see a function f of z is equal to 2x square plus y plus I into y square minus x. It looks like it is constructed by separating the real and imaginary part of it. Let's look at this, what happens. U is equal to 2x square plus y and v is equal to y square minus x. Here du by dx is equal to 4x and dv by dy is equal to 2y. So it can't be equal to each other unless point x and y both are 0. On the other hand, second condition, du by dy is equal to 1, dv by dx is equal to minus 1. This can never be 0, 1 can never be equal to minus 1, and this function is analytic nowhere. Well, this also we have seen, it's like a more or less an ad hoc function constructed, but it doesn't satisfy the Cauchy Riemann condition, and hence it is not analytic at any point. The Cauchy Riemann condition given earlier is in terms of Cartesian coordinate system. One can also do this in the polar coordinate system, as we see that sometimes it is convenient to have a complex function represented in terms of polar coordinate. So here you have f of z is equal to u of r and theta plus I times v of r and theta. The Cauchy Riemann condition in this case is u by dr is equal to 1 by r dv by d theta. And the second condition is, there seems to be a bug here. Let's try to fix it. Okay, the condition in this case is du by dr is equal to 1 by r dv by d theta, and the second condition is that dv by dr is equal to minus 1 by r du by d theta. So it is easy to show this with some algebra or transformation or writing r and theta in terms of x and y. One can show that. I leave this as a homework. So it is gives you both experience in computing the equation in a different coordinate system. Let's come to an important part of the Cauchy Riemann theorem, that is called the harmonic function. As far as the physics is concerned, this is one of the main application of a Cauchy Riemann condition. So let's first look at the definition of a harmonic function. A real valued function phi of x y in two variable x and y, first and second partial derivative exist in the domain D and satisfy the Laplace condition is said to be a harmonic in D. So that means harmonic functions are functions of two variable x and y. It should have a function and its first and second derivative should exist in the domain, and it should satisfy the Laplace equation. The Laplace equation is del square phi by del x square plus del square phi by del y square is equal to 0. So this is valid only in two dimension because we are connecting it with the complex variable. So it is not really extendable to 3-dimension or higher dimension. So we got to stick to 2-dimension or 2D geometry. Function satisfying the Laplace equation is extremely useful. We know that these are the potentials of electrostatic field in 2 dimension. We may also say the gravitational potential in 2 dimension too, but there is a bit of complexity there. We also have velocity field of incompressible and irrotational fluid in 2 dimension. You might not have done the fluid dynamics, but it can be shown that velocity of incompressible irrotational fluid in 2 dimensions satisfies the Laplace equation. So these two problems can be easily solved using the ideas of the complex number, or you can find out the field connected with the harmonic function or satisfying Laplace equation using the complex analysis. So there is no need to further impress upon this. This is an important topic from the physics point of view.